Okay, today we're going to look at sequences. Okay, so what is a sequence? Okay, well, here's a very simple sequence. We all know this one. I learned it a long time ago. Simply counting to 10 and beyond would be a sequence. Maybe go a bit more complicated, going up in twos. There's a clear pattern between the numbers. So this would also be a sequence. Okay, now look at a more complicated one. You might still recognize this. 1, 1, 2, 3, 5, 8, and so on. You might recognize this as the Fibonacci sequence. And this is defined recursively. That means that a value is dependent on the value, in this case, two values before it. So you can see here 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, and so each number is the sum of the two previous numbers. Let's have another, maybe slightly more complicated one. 1.1.01. Again, you can see each number is the number before divided by 10, or if you prefer, it's 0.1 to the power of what position it is in the sequence. So it'd be 0.1 to the 0, 0.1 to the 1, and so on and so on. Here's something that looks a little odd. Here's a sequence that at first glance it's very hard to see what the pattern might be, but sure enough it is actually a sequence, and we'll see later what that is. Okay, so here's our definition. So a sequence is a function an, but the domain is just the natural numbers. And the range is all the values that we can go to. So we take the terms to be a1, a2, and use the subscripts to define those. So that's our definition of a sequence. And so we can take a sequence from its nth term. So we give the nth term of a sequence, here we are, n factorial over 2n. We can actually find the sequence based on the nth term. So let's take the first few. So we'd get 1 factorial, then 2 times by 1, 2 factorial, 2 times by 2, and so on and so on. Now we can simplify this. Hopefully you're familiar with factorials. If you're not, just a little quick thing here. So remember, so for example, 5 factorial will be 5 times 4 times 3 times 2 times 1, all the way down to 1. Okay, so if we take those terms, and the 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and so on in the numerators. And then the denominators are just multiples of 2, because we have 2n down there, so 2, 4, 6, 8, 10. We can simplify this one more. Okay, that's how we would normally simplify these, where we have fractions. And that's okay, although we do lose the pattern a little bit. The one above, you can see what the pattern is a little bit easier than the one below. So whether you want to simplify like that might depend on the circumstances a little bit. Let's take another example, and we'll see this quite a lot as we go through sequences and series, this -1 to the n, or something similar. All this is going to do is alternate whether it's a plus or a minus. Okay, so when the n here is an even number, this will be a plus, be +1. But when the n here is an odd number, that would be -1. So that's going to alternate our sequence. So the terms of this sequence, -1, so the first term when we plug in 1, we get -1 to the 1, which is -1, and then 1 squared, which is 1, so it's -1. Whereas the next term when we plug in n equals 2, we get the -1 squared, so that just becomes a 1, and then 2 squared, of course, is 4, and so on and so on. So they alternate with the square numbers. Okay, so finding the sequence from the nth term is fairly straightforward. Finding the nth term from a sequence, however, is harder. If we take this sequence here, 5, 9, 13, 17, well, it's a little hard, but let's try and spot a pattern. Maybe we can see that the gaps here, the gaps between each value is 4. Okay, the gap between 5 and 9, 9 and 13, and so on is 4. So that's kind of a clue as what it might be. If it's going up 4 each time, maybe it's got a 4n in there. And sure enough, if we try 4n, well, it doesn't quite work, it's 1 more than that. So maybe an is 1 plus 4n. And once you've got that, we can easily check it, right? Plug in 1, we get 5, plug in 2, we get 9, and so on and so on and so on. Okay, so here's our very formal definition of the limit of a sequence, and this is something we're very interested in. In fact, again, throughout all of sequences and series, these limits are very important. So we let an be our sequence and L be some real number. We're going to take an epsilon, a positive epsilon. So actually really what this says is the gap between an and L will always be less than epsilon for any positive epsilon we choose for as long as n is big enough. This is what n is greater than m means. It's big enough, we can always make the epsilon smaller and smaller. And then that says the limit of that sequence approaches infinity. Sorry, as n approaches infinity is L. So the limit of the ANs is L as n approaches infinity. And if we can find a value L there, then we say that the sequence converges. If we can't find that, we say the sequence diverges. And that's important to note. Diverges doesn't mean goes to infinity, it simply not converges. We'll take a slightly more informal definition maybe. We say that the limit as n goes to infinity of an equals L if we can make the an's as close to L as we want for a big enough n. So the an's approach L. And again, we say that's true that the sequence converges. Okay, so let's take a look at the theorem that'll help us do that. Okay, so if an is a sequence and fx is a function where fn equals an, in other words, the function behaves like the sequence at the integers. As we go through, it'll be fairly obvious when this is true. So for example, if we had the an to be n squared, the f of x would simply be x squared. They're the corresponding functions and sequences from each other. And what this tells us is, if we know what the function does as x approaches infinity, we know the limit of that, then we also know the limit of the sequence. And this is going to be very handy. When we were finding horizontal asymptotes of functions, taking x going to infinity, we already kind of know how to do that, and we have a few rules and tricks for that. So if we can use these functions, then we should be able to find the limit of sequences when the sequence looks like the function. So let's take an example of this. Let's take an equals 1 over n. Okay, so here's the sequence, just the first few terms. So 1, 1 over 2, 1 over 3. Okay, that's fairly straightforward. I also recommend always, no matter what you're doing with these sequences, just take the first few terms. Just helps you look at how it's behaving, what it might be doing. Okay, and then we'll take the limit as n goes to infinity of 1 over n, and that appears to equal 0. We certainly know that if f of x is 1 over x, then the limit of that is 0. Therefore, from the previous theorem we just saw, then the limit of the sequence 1 over n must also be 0. So we can say that this sequence converges to 0. That was what we talked about before. Whereas cosine n, what does cosine n do? Well, cosine 1, cosine 2, cosine 3, they look kind of funny. If we actually evaluate them, remembering that we use working radians, 0.54, 0.42, negative 0.42, negative 0.99. It's a little hard to tell what's going on, and hopefully it's very clear. If you think about what cosine does, the shape of the function, that's never going to converge. It's never going to approach some regular value, and therefore we say that diverges. Okay, and again, we can think about what the function cosine of x does, which we know all about. That certainly doesn't converge, so neither will this. Okay, let's look at one more, and again this has this negative 1 to the n on the top, so we know it's going to be an alternating sequence, plus minus plus minus, or minus plus minus plus. Again, let's take the first few terms, and again it's very much like the one we've seen before, except with those minuses on every other term. Well, what happens? It kind of looks like it's going to 0, but it's a little more complicated this time. Those plus minuses, well, they confuse us a little. And we don't have a corresponding function to go with it. However, we do have a lovely theorem here. So we take this sequence, if we know that we take the absolute values of the terms, and that limit is 0, then the terms themselves go to 0. So if we take the case we have here, the minus 1 to the n, if we take the absolute value of those terms, well, the absolute value, all that really does is it drops the negative 1 from the top. Instead of going minus plus minus plus, it'll just be 1 over n. But we know that that one converges to 0. We just saw that just a second ago, so that one converges to 0 as well. Okay, that made that a lot easier. I mean, it's sort of intuitive. We thought that was what it was going to do. Okay, so we'll finish with our sequence we saw earlier. What does this do? 3, 3, 5, 4, 4, 3, 5. Well, let's think about counting. Let's think about the numbers 1, 2, 3, 4, 5. And in fact, sure enough, if we look at the number of letters in each of those numbers written out as words, Sure enough, that's what our sequence is, so we could keep going forever. Okay, so that's a very quick intro to sequences. There'll be a lot more that you'll see in class, but that'll do for now.